Now we are going to discuss in brief how liquid helium temperatures are achieved, or how does one liquefy the helium gas. For that, we are going to use the simple technique of Joule-Thomson effect, which we have already discussed. For that, we will take a porous plug. We will put helium, which is having a temperature below its inversion temperature. When this helium passes through this porous plug, the helium appearing on the other region is going to be cooler. Now this cooler helium is fed back again to the region 1, so that when it passes through the porous plug, it is further cooled. But note that this inversion temperature for helium is minus 240 degrees Celsius. So clearly, in order to maintain this helium below this particular value, we need to use liquid hydrogen for that. So the schematic setup looks like the diagram shown here. We see that this compressor sucks the helium contained in this tube, and this sucked helium is fed into this tube structure. Half of the tube structure is in contact with liquid hydrogen temperature, so that this helium has a temperature smaller than its inversion temperature. Once the helium is cooled below the inversion temperature, it is then provided at this plug G. Now this G is nothing but the porous plug. So when this helium having a temperature below the inversion temperature passes through the plug, gets cooled, and is available inside this tube in gaseous form. Now this cooled helium is again sucked by the compressor and fed back again into this tube structure, so that when it passes through this plug G, it gets again cooled. So this process is carried out continuously by running the compressor, and eventually the temperature after passing through this G is so low that helium gets liquefied and it starts to collect inside this tube. Since helium gets liquefied, the helium inside this tube becomes less and less. So there must be an external supply kept so that we get continuous supply of helium for this mechanism to work on. Now this liquefied helium can be collected in a Dewar flask. Note that though this Dewar flask is shown as a simple flask-like structure, we should note that it has to be maintained at least below this temperature Ti, so that the helium is available in liquid state. For that, this entire Dewar flask has to be contained in liquid hydrogen bath, and for that liquid hydrogen to be in liquid state, it has to be contained in liquid nitrogen bath. So this setup, which appears quite simple in this schematic diagram, is actually a quite complicated one and costs very much. There are certain properties, strange properties shown by liquid helium. When people saw that the temperature of 2.19 Kelvin is reached, and when the helium is cooled below this specific temperature, it shows certain strange properties. One of the important properties is the specific heat. So we get an abrupt change in specific heat at this particular point, and this abrupt change appears to be having a shape of lambda. So this temperature is sometimes called as lambda point. The helium behaves quite differently when the temperature is below 2.19 Kelvin. That type of helium is called as He2, and the liquid helium above this temperature is called as He1. Some of the strange properties exhibited by liquid helium below the lambda point temperature is superfluidity. That is, this helium shows no viscosity. So it cannot be contained in a container, and suppose there is helium contained in a container and there is a temperature gradient, then helium moves out of this container. So it forms a thin film on the surface of any solid in contact with it. So a typical effect connected to this is thermomechanical effect, which means that the liquid helium film moves from a region of lower temperature to a region of higher temperature. An effect exactly converse of this is also possible, which is called as mechanocaloric effect, where exactly opposite of this takes place. That is, if a liquid helium contained in a capillary flows, suppose there is a capillary and liquid helium is allowed to flow inside this capillary, then a temperature gradient is developed in a direction opposite to that of the flow of the liquid helium. So there are certain special effects associated with this liquid helium below the lambda point temperature, and obviously helium in this liquid state has some suitable applications as well. One can produce high vacuums of the order of 10 raised to minus 12 mm of Hg mercury. Since liquefying helium liquefies almost all of the gases contained in the air, so there is a closed tube and there is a liquid, there is a mixture of gases, that is air, present inside. If we liquefy this to liquid helium temperature, almost all the gases are getting liquefied, and then if we extract these liquid gases, then what is left in this closed tube is the vacuum, high vacuum. It can also be used to cool the high power electromagnets used mostly at the particle accelerators. Since liquid helium reduces the resistance of the coil, of these electromagnets is reduced, so it helps them conduct high current without the heating effect associated with the oscillating electrons inside the conductor. Further, it can also be used to construct bolometers, which are used in astronomy to study or to measure the heat coming from weak sources like stars, which are point sources of light. So in order to measure the heat coming from such small tiny point sources, the bolometer has to be very much sensitive and it has to be isolated from the fluctuations of heat received from the surroundings. That can be surely achieved with the help of liquid helium by maintaining the bolometer at such a low temperature which isolates it from the surroundings. It can also be used in computation, in fact computers, because the liquid helium temperature provides high operating speeds for computers. So these are some applications where liquid helium can be used. People are still exploring its uses, and the research is going on in this case. Thank you.